Now let's do a past homework problem, but I modified it to make it more complicated and integrate with your knowledge learned in transformation equations as well as the Mohr circle. The surface of an airplane wing is subject to the plane stress with normal stresses sigma x and sigma y as well as the tau xy. So here we know what is sigma x. At a counterclockwise angle, theta equals to 32 degrees from the x-axis. The normal stress is 37 milliPascal in tension. At an angle of theta equals to 48 degrees, the normal stress is 12 milliPascal in compression. It is given that sigma x equals to 110 milliPascal tension. We are going to find sigma y and the tau xy, as well as the principal stresses and maximum shear stresses. Besides, I want to construct the Mohr circle for the stress element and find the angle of inclination where the principal stress are occurred. You're also going to sketch the stress element. At the same time, you are going to verify there is no shear stress acting on the element by using the transformation equation when the principal stresses are occurred. Then, find the angle of inclination where the maximum shear stress is occurred by using Mohr circle. Sketch the stress element in this inclination. Besides, you are also going to show by using transformation equation that the shear stresses reach the maximum and the direct stress sigma x1 and sigma y1 are equal for element in part E. So there are a lot of parts, so let's try to solve them one by one. For first problem, you are going to find sigma y and the tau xy, and it is given sigma x1 in different angle of inclinations. Therefore, by using the transformation equations, we can write the following system. First, we put the sigma x1 on the left hand side. Then, since we know sigma x equals to 110 milliPascal, we also know theta, which is 32 degrees, and 48 degrees for the next case. So let's have a look of this transformation equation. For this transformation equation, it can be rewritten in this form, which is sigma x cosine squared theta plus sigma y sine squared theta plus tau sine 2 theta, where tau is just tau xy. Okay. Then we know that sigma x1 is given, theta is given, sigma x is also given. So now the variables left in this problem are just sigma y and the tau. In other words, if we can write two equations, then we can solve for sigma y and the tau immediately. In this problem, it gives you two groups of data for your calculation. That means you're going to use two equations to solve for tau and the sigma y. Firstly, substitute all what you know into the equation. At angle 32 degrees, sigma x1 equals to 37 and the theta equals to 32. We also know what is sigma x. Then you can write this equation with unknowns sigma y and tau. Similarly, for the 48 degree inclined case, sigma x1 equals to minus 12. Sigma x is known. Angle is 48 times 2. Okay. Then in this equation, the unknowns are just sigma y and the tau. With those information, you can rewrite the system to solve for tau and sigma y. It is about a lot of numerical operation works, but I think you can handle it. The answers are sigma y equals to minus 60.67 milliPascal, while the shear stress is given by minus 27.9 milliPascals. Next, you are going to find the principal stress and maximum shear stress on this element. Now you have already got tau xy as well as sigma y. Okay, so what you do is just to substitute everything into it. Then you can find the principal stresses. The principal stresses are 114.44 milliPascal and minus 65.12 milliPascal. At the same time, you can also find the maximum shear stress, which is given by R, but you know R is just the difference between the principal stresses divided by 2. Then the maximum shear stress is given by 89.78 milliPascals. Next, by using the results in the previous slides, you are going to construct the Mohr circle for the stress element, as well as find the angle of inclination where the principal stresses are occurred. You're also going to sketch the stress element at this inclination. So as we discussed previously, the equation for Mohr's circle is given by sigma x1 minus sigma average squared plus tau xy1 squared equals to r squared. To do this, first we find what is sigma the average direct stress. Well, it is easy to find. You know what is sigma x, you know what is sigma y. Then, by using sigma x plus sigma y divided by 2, you can find the average direct stress is given by 24.66 milliPascal. Also, by using the equation of r, the radius of the Mohr circle is found to be 89.78 milliPascals. In the previous parts, since we get at theta equals to 0, we know that sigma x1 equals to 110 milliPascals, and consequently we used our transformation equation to find that the shear stress is given by minus 27.9 milliPascals. So by using this Mohr circle, we can also verify that the shear stress we found in previous part is correct. First, suppose we don't know what is tau x1 y1, that is, we don't know what is it, okay? Then we locate a point on the Mohr circle where it represents that sigma equals to 110 milliPascals. So on this Mohr circle, the first principal stress is given by 114.4, while the second principal stress is given by minus 65.1. The reason is that sigma 1 equals to sigma average plus r, while sigma 2 equals to sigma average minus r. Then you can locate the center as well as the radius of the Mohr circle, and consequently you can find the principal stresses on the horizontal axis, sigma x1. By using our condition, sigma x equals to 110 milliPascal, we can locate the point at here. However, you may wonder, okay, for sigma x1 equals to 110 milliPascal, there is another possible point which is lying at here. Then why we can confirm, okay, it is located here instead of located here? The reason is that apart from considering the 110 milliPascal direct stress, we also consider the two given conditions, which is at 32 degrees, the direct stress is given by 37 milliPascal, while at 48 degrees, the direct stress is negative 12. So let's consider those two cases to see which one is correct. So for this case, if we consider theta equals to 48 degrees, then supposed by what the condition is given, sigma x1 equals to minus 12 milliPascal. Let's try to rotate this line by 96 degrees. Then significantly, it will lie in some region like this. Okay, and this point represents that, okay, the sigma x1 is slightly negative. However, if we are talking about this point, if we say okay, theta is 0 here, then by rotating 96 degrees, you can see, okay, it is actually not making sense as the sigma x1 is not negative 12. You can also verify by using the data of theta equals to 32 degrees. So still being in mind that for the angle here, it represents 2 theta instead of theta. So for theta equals to 48 degrees, we rotate by 96 degrees of this line, okay? And similarly, for theta equals to 32 degrees, we rotate this line by 64 degrees. Also, at this point, we know that direct stress is 110 milliPascal. Then we can compute tau xy directly by using the geometry of the circle. So we substitute sigma x into this equation. At the same time, we know what is the radius of the circle. Therefore, we can compute tau x1 y1 by using the formula. The result will be negative 27.9, which agrees with our results previously. So our result after solving this system is given by negative 27.9 milliPascal. So it is exactly the same to what we found from the Mohr circle. Notice that although this point is lying above the horizontal axis, but still recall that we adopt the vertical axis to be reversed. That is, for a point lying above the horizontal axis, it represents a negative shear stress. Therefore, we can find alpha, which is the angle between this line as well as the horizontal axis. Alpha equals to arc cosine 110 million Pascal minus 24.66, which is the average direct stress, divided by radius. The result is 18.1 degrees. Consequently, we can find the principal stresses. So recall that principal stresses is the maxima and the minima of direct stress. The principal stresses are located here and here. Here we call it sigma 1, while here we call it sigma 2. For sigma 2, it has a principal angle of theta p2. Here it represents theta equals to 0. Then 2 theta p2 represents this angle from theta equals to 0 to the second principal stress, which the value is Mohr. 2 theta p2 is around 162 degrees, then theta p2 equals to 80.9 degrees. Similarly, for sigma 1, we consider this angle. This angle represents 2 theta p1, but it is just adding 180 degrees from 2 theta p2. Therefore, theta p1 equals to 80.9 degrees plus 90 degrees equals to 170.9 degrees. After we getting theta p2 and theta p1, we can construct the sketch of this stress element. Rotating this stress element counterclockwise by an angle of 80.9 degrees means that those two surfaces represents 80.9 degrees, while those two surfaces represents 170.9 degrees. So to do this, first, for 80.9 degrees surfaces, we know that the principal stresses is given by minus 65.1, which means the stresses on 80.9 degree surfaces are 65.1 million Pascal in compression. At the same time, for the 170.9 degree surface, the principal stress is given by 114.4 million Pascal in tension. Next, we try to verify that there is no shear stress acting on the element in C by using the transformation equation. That is, we are going to prove that for the principal stresses, that is, the maximum direct stress occurs, there is no shear stress acting on the stress element. As what we predicted in the previous slide, there is no shear stress. To do this, we just substitute those two angles into the transformation equations, as well as what we got for tau xy, sigma x and sigma y. We substitute everything inside this transformation equation, and eventually we get 0. How about the angle of inclination where the maximum shear stress is occurred? Try by using the Mohr circle. So for the maximum shear stress, observe that this Mohr circle is symmetrical about sigma x1 axis. To do this, we draw a vertical line which passes through the center of the Mohr circle. It is significant that those 2 points represents the maximum and the minimum shear stresses, but actually, the shear stresses are just equal in magnitude. So on this vertical line, you can obtain the maximum shear stress. To do this, first, we know that 2 theta s equals to 90 degrees minus alpha, then theta s equals to 35.95 degrees, and similarly, theta s2 equals to 35.95 degrees plus 90 degrees, but actually there is nothing that we can do with it because this surface is 35.95, but adding 90 degrees is automatically this surface, so actually there is no much thing we can do because we suppose the stress element is a square. Then we can also sketch the stress element at this inclination. We found that the direct stress acting on the stress element in x1 and y1 directions are the same, which is 24.7 million pascals. We also know that the shear stress acting on the stress element is given by 89.8. Then we can sketch the stress element like this. So notice that all the units in the sketch is million Pascal. Finally, you are going to use the transformation equation to show that all your conclusions in the previous part is correct. So it asks you to show that the shear stress attains the maximum, as well as you are going to show that the direct stress on x1 and y1 directions are the same. To do this, we substitute theta s1 into the transformation equations of the direct stresses. You will get the same answer, which is 24.66 million pascals. You repeat the above procedures by using theta s2, substitute it into the transformation equations, you can get the same answers. To show that the shear stress reached the maximum, you are going to use the transformation equation in this way. First, you have your transformation equation, then differentiate your transformation equation with respect to theta. You will get this expression. Then you are going to substitute the value of theta s1 and theta s2 into d tau d theta. Then, if the result is 0, then you are successfully verified that what you have found is the maximum.